So today I'm going to start with the chapter 13 comprehension checks. This chapter is titled The Heat is On, and it is all about what we call thermochemistry, which is basically studying how heat is transferred throughout chemistry. And so to understand what these questions are, the first thing that you really need to understand is what is heat. So heat is energy that is exchanged due to either a temperature difference or a phase change. And we're going to talk more about that when we move into question number 2. But the first comprehension check, question number 1, tells us that you have two solid blocks and they're the same exact temperature and they're placed in contact with each other. And is heat being produced? Well, heat is when we actually are exchanging energy and we have a temperature change. But if I have two blocks and they have the same energy, and so the key is that they have an equal temperature, there is no heat being produced because there is no energy being exchanged. So the answer is no. So question number 2 tells me I have a mixture of ice and water, just a good glass of water. And the ice is actually melting, which is what happens when you put ice in a glass of water, especially because it's hot as it does here in Tennessee. And the temperature though is staying the same. And is there heat? Now remember we talked about heat happening when we have an exchange of energy due to either a temperature change, but I don't have a temperature change here, but it also can happen when you're having a change in energy due to a phase change. And so what is actually happening in your glass of water is your ice is slowly going from being a solid to a liquid, and so it is actually having that phase change. And if you know when something goes from a solid to a liquid, it is actually gaining energy because it takes energy for that phase change to happen, because liquids have more energy than solids. And so since we are having an exchange of energy, there is heat happening in a glass. Before we get to question number 3, I need to introduce you to what a calorie is. And when we have calories in chemistry, they're a little bit different than the calories that you're used to reading on the back package of like food labels. So a calorie is the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius. I know in the past chapter or in 2 chapters ago when we were dealing with gas laws, all your temperatures had to be in the Kelvin system, but right now we're going to be using Celsius. So the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius is a calorie. Now, I wrote a conversion unit up here that you need to learn or write down on your note card. I'll go over some of the equations later. But 1 calorie with a capital C is a food calorie. That is actually equal to 1,000 what we consider chemistry calories, or calories with a lowercase c. So if you were to take like 1 food calorie, that is 1,000 chemistry calories. So let's look at question number 3. This is one of the weirdest questions I think in this book. So the book specifically says you go to McDonald's and you get a quarter pounder with cheese hamburger. And it has about 500 capital C calories or food calories in that hamburger. And so then we're taking this hamburger and you're going to be burning it essentially under 10 liters of water. And so the water is at an initial temperature of 25 degrees Celsius. And as you're burning your hamburger, I can just envision what that would smell like. The water is going to be raising its temperature. And so it's asking me, what is the change in the temperature going to be? And so what happens is you're taking the energy from this hamburger and you're converting it and putting this energy into the water above it. And you're going to see the energy change the temperature of the water. Now, if we know we're dealing with calories, and I know a calorie is what can raise 1 gram of something 1 degree Celsius, I actually need to know grams. And this question gives it to you not in grams, but it says that you have 10 liters of water. And so we're going to take some of our knowledge from like chapter 1 essentially at this point and see if we're going to take the 10 liters and we need to go to grams. And so the first thing I'm going to use is I'm actually going to use the density of water. And then you should remember the density of water. If not, I think it actually talks about it in the chapter. So to calculate the density, if you'll remember, I taught you this little triangle in like the first chapter, and we said the DMV, it's where you go to get your driver's license, but it's density, mass, and volume. So if I'm solving for density, I'm going to cover up the D and I have mass over volume. So the formula I'm going to use is density is mass over volume. Now, the density for water is 1. But for this equation, I'm actually looking for the mass. And so if I'll cover up the mass, I end up with density times volume. So my mass is equal to the density times the volume. Now the density for water is just 1. And the unit for that is grams per milliliter. And since it's in milliliters, when I put my volume in, I also have to put my volume in milliliters. And so if you'll remember, if I'm taking 10 liters to milliliters, I'm in liters. And if I'm doing king, hair, dye, drinking chocolate milk, I'm going to go 1, 2, 3. So you're actually going to move your decimal point 3 times. So 1, 2, 3, and then fill in the zeros. So now if I'm solving for the mass, this is milliliters, so milliliters cancels out. And in my 10 liters of water, I actually have 10,000 grams of water. Now I have this in grams and I'm dealing with calories or chemistry calories. It's temperatures in Celsius, which they've already given me the temperature in Celsius. I have grams. So we need to put this in chemistry calories. So now that I'm going to convert from food calories to chemistry calories, this is a little tricky because those C's look the same if they're big or little, but 500 food calories with a capital C is equal to 1,000 chemistry calories. And so I'm going to put the 1 capital C calorie at the bottom, so that cancels out. And I have 500,000 chemistry calories. So I have my hamburger with 500,000 chemistry calories. And now we just have to kind of logically think this problem through. So if every calorie raises up 1 gram of water 1 degree Celsius, well, I don't have 1 gram of water. I have 10,000 grams of water. So it will take 10,000 calories to raise this 10,000 grams of water up 1 degree Celsius. So how many calories do I have? If it takes 10,000 to raise it up a degree, well, if I take this number and divide it by this 10,000, I get 50. So I have 50 10,000s in there. And so actually my temperature is going to go up 50 degrees Celsius. So it's not going to have 25 degrees Celsius. It's going to be at 75 degrees Celsius. If you do not understand this comprehension check problem, do not worry about it. This problem is very odd to me and it doesn't really fit in very well. They just are trying to get you to understand the concept of 1 calorie in this problem. So before we get into question number 4, I need to introduce you to the concept of specific heat capacity. And specific heat capacity is the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius. And so something you will actually have to learn is that it takes 4.184 joules of energy to raise 1 gram of water 1 degree Celsius. There's a list of these in your book on page 392, and they tell you exactly how much heat it takes to raise 1 gram of a bunch of different elements 1 degree Celsius. And so for question number 4, it tells us that equal amounts of energy are removed from equal masses of, and then they give me a sample of silver, lead, zinc, copper, and if you're in America, we say aluminum. If you're in, I know at least in Uganda, they say aluminium. But basically, I have a same size substance and I'm changing its temperature or it's cooling down the same amount every time. And so I am wanting to compare the specific heat capacities for all of these elements, and then we can decide which one's going to be the warmest and which one's going to be the coolest. So just imagine we have a same size sample of each of these metals and I'm removing the same amount of energy, but they're actually going to have different temperatures at the end because some substances have the ability to absorb heat without a huge change in temperature. We see this with water. Water can absorb a lot of heat before it gets really hot. That's why we use water to cool things down. Some numbers from page 392 in your book. All right, so when I take these numbers from the book, if you'll notice, they all have a unit of joule per grams degrees Celsius. And this is essentially the amount of energy that it takes to raise the temperature of this 1 gram, 1 degree Celsius. And so if it takes a lot of energy for it to raise its temperature, you're not going to see its temperature go up really fast. So the question is asking us for which item is going to stay the warmest and which item is going to stay the coolest. So the lowest specific heat capacity is 0.160 is lead. The lowest specific heat capacity, it means it's easier to heat up and it's easier to cool down. So this one is going to be the coolest. And the one with the highest is aluminum. And since it has the highest, it is going to be the hardest to heat up or to cool down. And so it's going to keep its temperature and it's going to be the warmest still. And so if you can compare aluminum or aluminum at 0.9 to the specific heat of water, which is 4.8, there's a big difference there. So that ought to give you a hint about how hard it can be to heat water up. You'll remember the specific heat capacity is just the amount of energy it takes to raise 1 gram of a substance 1 degree Celsius. And so if it has a higher number, it's harder for it to heat up or cool. It takes more energy. And if it has a lower number, it's easier for it to heat up or cool down. So to work question number 5, you need to be introduced to a formula that we use in chemistry to calculate heat. And so you're going to get this formula. You see it in the book. It's the top formula. It's Q equals MC delta T. So we use Q actually for heat. That's our heat transfer. In our heat, it's given to us in joules usually because heat is energy. Then M is our mass of our compound. C is the specific heat capacity, which we just talked about, and delta T is the difference in temperature. So we're going to use these equations because there may be a time in science where you actually have a compound or an unknown metal and you're trying to figure out what it is. Well, from the last question where we had specific heats and we were just looking at them up in a table, the specific heat of certain metals or of elements is known, and it's actually usually written down in a table in a book or on the computer. You could look it up on the computer. So by actually doing a formula or an experiment, you could figure out the specific heat of your compound, and then you could go look it up and you could actually figure out what that metal was. So you could do an experiment similar to like the hamburger one. You could figure out like how much heat it produces off and calculate the specific heat. And then you would know exactly what your metal is. And so to do that, we would use the heat equation, Q equals MC delta T. And so that's going to be the equation you're going to start using for the rest of this chapter. And so for this one, we have a 1.5 kilogram object and it's been heated up. And now it's cooling down. And so it's going from 22.5 degrees Celsius to 8.1 degrees Celsius. And as it's doing that, it's losing 6.3 kilojoules of energy. And the question is asking, what is the specific heat capacity? And so specific heat capacity is the C. So they give me the Q, which is heat transfer. They just give it to me in kilojoules. That's the energy. They tell you the mass. You're looking for the C, and we can calculate the difference in temperature. And so the difference in temperature is just the final temperature minus the initial temperature. So in order to really put all these things in, we have to make sure that everything is in the correct unit, similar to like our gas laws and all these other equations. One of the ways that I remember the units for the specific heats is that if I look at the specific heat for water and I know it's in joules, grams, and degrees Celsius. So everything I put into this formula has to be in joules, grams, or degrees Celsius. But for the Q or the heat, it's actually given to you in 6.3 kilojoules. You're just going to move your decimal over. Then the mass, it's in grams, and so I need to get 1.5 kilograms into grams. So I'm gonna move my decimal place over. 1, 2, 3. C, I'm looking for, so I do not know it. And then delta T can be easily calculated. So it is the final temperature, which is 8.1, minus the initial, which is 22.5. You actually are going to get a negative for this. And so make sure that's in Celsius, and it makes sense that you get a negative because this temperature, it's cooling down, it's going down. So I'm just going to take this and put it in here. Now, once we've gotten all of our information put in our equation, the only other thing we need to talk about is that this is actually losing energy. And so since it's losing energy, we're going to put a negative in front of the energy. So now I'm going to solve for C. So I basically would just take both of these and divide it by this. So you would have now, when I put this in my calculator, I would put it in one step. That way you're less likely to make a rounding mistake. So go ahead and put in the negative 6,300 and then divide it in all of the bottom in parentheses. And you should get 0.29 joules per grams degrees Celsius. And if you were curious as to what your metal was, you could then take that information and go look it up. Comprehension check question 6 tells me I have an object that is made up of nickel, and I'm taking this object and I'm actually heating it up, and I know that temperature is going from 23.4 degrees Celsius to 44.3 degrees Celsius. And it knows that by heating it up, I'm actually adding 987 joules of energy into it. And so the question is asking me, what is the mass of this piece of nickel? And they give you the specific heat. And so this is another Q equals MC delta T problem. So if Q is the heat, they actually tell me, and they actually even give it to you in joules this time. So, and you are actually raising the temperature, so the heat is going to be positive. So it's just 987 is Q. The mass, I don't know. I'm looking for it. C is given to me. And delta T, I can actually calculate. So the final is 44.3, and the initial is 23.4. So you would just do the subtraction. 20.9 degrees Celsius. So now we would just solve for M. $987, then you would put 0.440 times 20.9 in parentheses on the bottom of that. And for M, you should get 107. And this is a mass, and so it is in grams. Why no decimals to that answer? Well, here I have 3 significant figures. Here I have 3 significant figures, and here I have 3 significant figures. So my answer is going to only have 3 significant figures. Assumes that you know what a calorimeter is. So I'm going to show you one, and we're going to talk about what its parts. So this is kind of what a science calorimeter looks like. You may do one in lab where it's just a coffee cup, to be honest, and that does pretty good. But it has top, and in the top you have an insulated layer. I think this one's just insulated with like a styrofoam piece. And then your top. This top has this piece here to mix with. And there's a hole for a thermometer. Now, there is a piece it comes with that you can attach it to an electrical source, and you can put heat into the calorimeter. We actually don't do that usually in high school, but sometimes you'll see that piece. So what you use this for is if you have a piece of a metal and you don't know what it is and you're wanting to know exactly what that metal is. So we do this in lab where you take your metal and you heat it up. We actually use boiling water. You heat it up to about 100 degrees Celsius. And you will put it into then your calorimeter in water. with the thermometer. And so what's going to happen as you take that piece of hot metal is it's going to transfer its heat into the water of the calorimeter, and you'll see the temperature go up. And then we can calculate back to figure out the specific heat of the metal to look up what the metal is. Now, we can do that by knowing the amount of heat that we put into the calorimeter, and then you can know the mass of the metal, the specific heat, which is usually what we're looking for, and the temperature difference. So you're watching the temperature go up on the thermometer. Now, all of those are pretty easy to get except for Q. It's hard to know exactly how much heat was put in that metal for the metal to give back to the calorimeter. And so we have an equation that we use for that. And the equation is negative Q of the object, so the heat of the object, and it's negative because the chunk of metal is actually, when you put it in here, it's losing heat. And so that heat then goes into the water in the calorimeter, and then some of it actually gets absorbed into the calorimeter. And you know that from if you've had a cup of coffee and hold your hands on the outside of it, your hands will get some of the heat too. And so there is heat goes from the metal into the liquid and into some of the sides of the calorimeter. And so we can then calculate the exact heat of the object to put it into Q equals MC delta T. Now, where this gets, like a lot of times in these equations, they're going to tell you to ignore the calorimeter part, which means we're going to assume our calorimeter is not absorbing any of our heat that is happening. Now, odds are that's not, you are actually absorbing some heat into the calorimeter, but it just makes the math a lot easier. In question 7, we have a 200-gram sample of an unknown metal. We're putting it in our calorimeter. Our calorimeter has in it 115 grams of water, and it's starting at 24.1 degrees Celsius. So we're heating our metal up to 110 degrees Celsius, and then we're putting it into the calorimeter. And we get to our final temperature of water at 26.3 degrees Celsius. We know it's the final temperature because as you're watching on that thermometer, that is where it's like it'll hit that degree and then it'll slowly start to go down. And so we're looking for the specific heat of the metal. And so to find the specific heat of the metal, I need to be able to answer Q, M, and delta T. Now they told me the mass. I know the mass of the metal. And they told me the temperature difference, right? I know the metal is going from being 110 degrees. And so let's see what we need to calculate to find the Q. And they actually tell you to ignore the calorimeter. So therefore, I know that the heat of the object is going to be the same as the energy of the object is going to be the same energy that goes into the water. So the metal loses its energy and it goes into the water. So I can calculate the heat for the water and then use that to figure out the object. So for water, if you know, Q equals MC delta T. I don't know Q, that's what I'm looking for. But I do know the mass of the water. It's 115 grams. And I actually know C for water because it's something you just have to know or write down, 4.184. And the temperature difference of water. So the water is going from 26.3 is the final minus 24.1. And so the temperature difference is 2.2 degrees Celsius. So Celsius cancel out, grams cancel out. And I'm just going to multiply those across and I will get an answer in joules. And that's the heat that goes into the water. I'm only going to keep 2 significant figures. The reason I'm doing that is because I have 2 significant figures in my temperature. And so I have a Q for the water is 1,100 joules. Now, I would normally put this into this equation. And so I know that the object then lost 1,100 joules because the equation told me to ignore the calorimeter. Now I want to find Q equals MC delta T for the metal object. So I know the Q because the object lost, the metal lost heat, so it's negative. The mass of the metal is 200 grams. So I'm going to put in joules 1,100. It is negative because it's losing the heat. Then I know the chunk of metal has 200 grams. C is what I'm solving for. And the temperature change for the metal is 83 because the metal goes from 110 to 26.3. It is 83.7 and it's negative. Because the metal, sorry, I said that backwards. It's 26.3 minus 110, which is how you get a negative number. So when you do 1,100, and I would divide it, put parentheses around 200 times negative 83.7. Remember, there's a negative up here too. And you should get 0.66. And remember, this is a specific heat, so it is in joules over grams degrees Celsius.